Welcome to my talk. In this talk, I'm going to introduce to the RealAIGym project. So RealAIGym is an education and research platform for studying athletic intelligence. So we are specifically interested in highly dynamic robots and how can we combine different approaches from model-based control and model-free control to achieve the next generation athletic intelligence. Based on this platform, we had defined this competition, which we titled as AI Olympics with RealAIGym, and in this talk, we will see a bit about both of them. So this is the outline of my presentation. First, I will talk about the motivation of this RealAIGym project, and then talk about the systems that we have developed under this framework. So it starts with very simple systems like simple pendulum, double pendulum, and then it goes on to systems which can exploit those swings to achieve some locomotion behavior, in particular brachiation. So we can do monkey bars, and then we have legged systems which can do hopping and parkour. And then I will talk about the AI Olympics competition that was conducted at IJCAI based on this ecosystem of underactuated systems. So let's get started. So we are witnessing a real revolution in robotics at the moment. So just 10 years ago, it was hard to find robots that can move similar to animals. But now we have a bunch of them. So in this picture, you see Atlas, the famous Atlas humanoid robot from Boston Dynamics. Then we have Cassie or Digit from Agility Robotics, and the MIT Mini Cheetah robot, which was one of the first robots that showed an impressive backflip. So some common features about these robots are that they are underactuated systems. That means you can't control all their degrees of freedom. They are capable of dynamic movements. They show some kind of compliant behaviors, which are important for dealing with contacts, and they are robust to impacts and contact forces. Okay, so why did we want to build this project? Well, what we have seen is that you can achieve impressive performance on robots through a wide variety of control methods. Even during the keynotes, you saw that we had very high-level AI-based or heuristic-based methods which work on walking robots, but then we have reinforcement learning approaches which exploit some structure in the robot data to achieve this, and then we have model-based control method which exploit full structure. And these are all like different communities. Each have had some success to control these kind of systems, but it's really hard to compare these methods because reproducibility is an issue in robotics research. And hence we decided to build a education and research platform which basically consists various canonical underactuated robotic systems which you can use to test state-of-the-art controllers in a fair and reproducible manner. So in this picture you see some of the systems that we have developed. Some of them have been open sourced already, some not. So while designing this project, we had several topics in mind. We wanted to keep the systems low cost, so that we can basically 3D print most of the parts in a lab, and other research labs can reproduce these systems. There are commercial systems in the market, but they are usually expensive, and they often work in conjugation with proprietary software like MATLAB and Simulink, which can be hard to acquire by many research labs. We also wanted to keep the entry barrier small, so we decided to use Python 3 as the main programming language because Python is now used by everyone in machine learning, AI community, and also it's getting more and more popular in robotics. And it helps people quickly prototype controllers and test them. Reproducibility is a big topic that we care about, and hence we decided to have some standardized hardware and also have well-documented software. We want to achieve an end-to-end open source system. That means we provide transparency at all levels, including the motor firmware, communication protocols, controllers, and so on. And this is the basis for reproducibility and education. We provide already a bunch of built-in controllers, starting from heuristics, classical control, model-based control, and also reinforcement learning. We provide a benchmarking environment with every system so that we can basically compare different controllers against the same set of metrics. And we want to promote the use of this ecosystem in education and research. For the motor drives, we have selected quasi-direct drives. So these actuators, they allow us to achieve highly dynamic motion control. The main idea is that they have low gear ratios. That means you have high mechanical transparency, and you can achieve high velocities and good torque control. We provide an interface in Python which allows the control of these motors up to 1.5 kilohertz. Okay, so some examples of what I mean by athletic intelligence. So I think we as humans or animals, we are really good in tapping the dynamics of swings. I think also Boris mentioned this in his talk, that he categorized the behaviors into stroke and rhythmic behaviors. And here you see some examples of that, right? So it's me on a swing in a park in Bremen. And I'm using a little bit of forces from my legs in order to build more and more energy, right? In the second example, you see an Acrobat which performs a swing up. Now, if you look at this Acrobat, he does not have enough torque in the wrist, but it's building energy by swinging its body, like torso. And then you see an example of a guy who performs a backflip on a single leg. And then we have a monkey which can basically brachiate across monkey bars in a very elegant manner. So we built our robotic role models for these systems. So first we have a torque limited simple pendulum. I think I'm gonna reduce the volume a bit so that it's not too annoying. So the torque limited simple pendulum has limited torque, and the task is to perform a swing up. Then we have the double pendulum where we are only using one actuator, and the task is to again perform a swing up. We have this vertical hopping leg contraption which can jump to any given height, and it can perform a backflip. And then we have this Acromonk robot which can basically perform brachiation across monkey bars. Okay, now we will go through each of these systems, and I will show you the progress that we have achieved with them. So the first example is that of a human on a swing, right? So as I said, I apply little force in every swing with my legs to achieve higher swing angles, right? And since I'm on a swing and the chain can go slack, right? So I cannot do a swing up, but I can try to reach the horizontal line. But we don't have this constraint on the real robot. So now, if the motor has enough torque available, then basically you can command it with a PID controller to go to the top position. But if the motor does not have sufficient torque, then there is no way it can go up with a simple PID controller. And that's where you need to use smarter methods or energy-based reasoning to go up. So here we see an energy shaping control which basically puts a little bit of torque in every swing so that it builds energy as it is swinging, very similar to what I was doing when I was on swing. And it can also go up and stabilize itself on the unstable fixed point with an LQR controller. So this is pretty much a textbook example, right? And we have implemented this on the real system, and living by the promises of this project, we have provided really a variety of controllers. So you can see we have methods from trajectory optimization, reinforcement learning, policy-based control, trajectory-based control, all integrated with a single open source plant definition that you can use as a simulator or for the real world control, and then you can talk to the hardware in the same ecosystem. So here is an example of the benchmarking that we had done on the simple pendulum. So here you see a comparison of 10 different approaches on various different metrics. For example, swing up time, how much energy the controller needs, how smooth is the controller, what was the maximum torque used by it, robustness to disturbances, and so on. And yeah, it's a well-documented project. So if you go to any repository, you will find online documentation, and we have made sure that it's easy to understand and the system is easy to reproduce. We also provide open source CAD models and all the electrical diagrams in case a lab wants to reproduce the system, as well as the theory behind the controllers, and of course the references, extended references for each system. Okay, the next system in the swings category is inspired from an Acrobat. So here you see this Olympic gymnast doing a swing up, and we achieved this with our double pendulum system. Classically, this has been studied in two different ways, Acrobat and Pendubot, and you will find different hardware systems for each of these applications. But because of these advent of the quasi-direct drives, we can basically switch off one motor and use it as a passive encoder. So this was not possible before. If you look at previous Acrobat and Pendubot implementations, then you will see that yeah, there is only an encoder, and they often mount the motor at the elbow at the base and use some belt drives to create the transmission. But now, because of the quasi-direct drive, we can implement a very simple system, and they have low friction. So here is a time-lapse or long exposure photo of a free fall of the double pendulum, and you can see the chaos that is present in the system. So this is just an electrical diagram. I'm not going to go through it, but it's all very simple to set up. You don't need much infrastructure to develop this. And in order to challenge, let's say, our controllers, we have also done region of attraction analysis, which tells us which configuration of the Acrobat or Pendubot is more difficult. So what you can see in this diagram is that the region of attraction of the Acrobat, which is at the top, is much smaller than the Pendubot. But by changing the link lengths, you can actually come up with hard Pendubot, easy Pendubot versus hard Acrobat and easy Acrobat. Since we want our controllers to be robust, we also wrote modules for testing the robustness with respect to model parameters, for example. So these were the variations, and you can see here the success of, I think, the iterative LQR controller, MPC controller. And yeah, basically you can evaluate any controller based on these variations. So here you see a comparison of 5 different controllers. We have time varying LQR, iterative LQR, 3 variants of iterative LQR controller, and the classical partial feedback linearization, which was proposed by Spong for this system. And then you can see the robustness of all these controllers with respect to variations in the model parameters, the noise in the velocity measurement, the noise in the torque measurements, the torque response and the delay, communication delay, which are things that we come across when we want to transfer any policy or a controller to a real system. And in this video, you will see the swing up and the stabilization that we achieved on the first version of this system. So this is the Acrobat example, and here it is performing a swing up, and this is the result of an iterative LQR based trajectory optimization. And now you will see the video for the LQR based stabilization. So it does quite a lot of bang control, as you can see in the torque signal, but nonetheless it's stable at the top. And like this was the issue that I was telling you, because of vibrations in the mechanical structure, it was causing instability, and this issue was then addressed by some design changes. And now you see the swing up of the PenduBot. So here, yeah, it swings and then goes up. Again, it's the same approach, iterative LQR based trajectory optimization and an LQR controller on the top. And it's also robust to disturbances. So you can hit it with a stick, and yeah, it can reject those disturbances. All right. So now I will show the next category of robots. So these are inspired from monkeys, which can brachiate across monkey bars, right? So what we have done is that we developed, actually the idea originated in the implementation of Acrobat. We decided to simply turn our Acrobat into a monkey, and we designed some passive grippers, and you have an actuator already in the torso, right? And the idea was to now swing between bars using the control approaches that we have been studying for Acrobat. Yeah, and here what you see is that we developed some kind of robust state machine which helps the robot to achieve that. So by composing 4 different behaviors, like going from a hanging position to the front bar or the back bar, and then going from front to back or back to front, we can generate robust brachiation behavior. And again, we did this with model-based optimal control methods and also reinforcement learning. So here you see a video of this robot implementation. So by the way, this work is going to be presented at IROS this year. It was accepted in the IEEE Robotics and Automation letters. So you see that the whole robot can be 3D printed here. It's very simple parts, just one motor, passive grippers. So it's a system that is very easy to maintain, easy to carry. You can fit it in a backpack. And yeah, it's robust to contacts and falls. And yeah, here you see the robot doing brachiation across multiple monkey bars. And now you will see how it works. So we have some heuristic based controllers for catch and release. So here we apply some torque on the motor in order to release, and the gripper design was optimized in a way that it has some natural region of attraction. So as long as you are inside that region of attraction, the gripper kind of snaps onto the bar, and this helps in achieving like you saw here, right? It was a little bit inaccurate, but because of the passive dynamics, it snaps automatically. And now you will see these 4 different atomic behaviors that I was talking about, right? So going from back to the front bar, and similarly you can have front to back, like to do a backward brachiation. And next you will see 0 to back. So this is when by chance, if you fail during brachiation, right, you would end up hanging on the bar. So this is like a recovery maneuver to go either to the back or the front bar. So this is the 0 to front maneuver. Yeah. So now if you have these 4 things, then you can easily do a robust brachiation. So combining all this, we can get forward brachiation. So this is what you see in this video. Then the same thing is achieved with a time-varying linear quadratic regulator. So the previous video was PD control. And then we did the same thing with a model-free reinforcement learning controller. Yeah, and we made a comparison across all these approaches, compared the transport duration, success rate, energy consumption, and so on. And finally, here you see the acromonk trying to meet his friend on the other side in the jungle. So here you see that we are disturbing it, and it fails. So it goes to this 0 hanging posture. And now this state machine is triggered, so it knows where it has to go. So yeah, it starts to. So you can be mean to the system, but it will always succeed. And we can also give you like guarantees about the controller, because we use a model-based approach. So you can compute the region of attraction, and we can quantify what level of disturbances the robot will always succeed with, and where it needs to rely on this state machine reasoning. So recently we also built a brother of acromonk. We call it RickMonk, and this is a 3-link brachiation system. So you see now we have 2 arms with 1 passive body. And the reason why we developed this system is to see if the passive tail helps in more energy efficient brachiation. So this is a very fresh piece of work, but it's going to be integrated in the RealAIGym, where we test and benchmark different controllers. Now, when it comes to Leggett system, again, we were interested in studying hopping and walking and running, these kind of behaviors, right? So here's one example from the nature where a kangaroo is hopping around in some grasslands. And in order to study this, we first started with a vertical hopping leg. It has 3 degrees of freedom, 2 active degrees of freedom, and 1 passive degree of freedom on the tail. And the task is to achieve stable hopping heights. So the input should be that hop at this height, and then the system should be able to do that, right? And again, just to we talk about all this reinforcement learning and model-based control, but sometimes very simple heuristics are powerful enough to enable these kind of behaviors. So the most, stupid way to do this could be that you just take the feet of the robot and you give a sinusoidal trajectory. And if you do that fast enough and you get into some conditions with the gravity vector that is acting on the system, it will leave the ground and start hopping. So that's the most basic thing, right? But then you can do something more fancy, that you can schedule gains. For example, when you are landing on the ground, then you damp it so that you absorb the impact better, right? And when you are leaving, you stiffen your leg. And eventually you can do the same idea of energy shaping that we had for the swing up problems, right? This can be extended here. And yeah, we implemented all these methods. They all work fine. But of course, the energy-based method is the best working one here. And here you can see the robot jumping at a height of 0.6 or 0.55 meters. And it can even jump and like perform a backflip. Yeah. And all of this is proprioceptive control. So there is no like force torque sensor, camera, or it's just motor measurements which is used. We also implemented a reinforcement learning based approach to do the same. And I think to our best knowledge, this is the first end-to-end RL framework to achieve variable height hopping. And this work is also going to be presented at IROS this year. Yeah, but our idea was like, when you do this energy-based control, then you have to implement the state machine, and you need a lot of human expert knowledge to tune the gains and so far, so on, right? Can you have like one policy which does all of that purely from the torque measurements, position and velocity measurements, and torque as the output? So we have no PD control running anywhere. The policy is just directly outputting motor torques, and it takes as input the position and velocity measurements of the joints, right? Because in our energy shaping control, we have a simple like ball bouncing model which does the state estimation for the heights. And if it's possible to like put in this human knowledge there, then can we discover that with an RL policy, right? And that was the thought process behind this work, and we were able to get some good success. So you can see here we are providing different hopping heights, and the robot is able to jump. Of course, the tracking accuracy is not that great like in energy shaping control, so there is still room for improvement. But in principle, we were able to show that you can do this in such an end-to-end fashion. Okay, I think I'm running a bit behind the schedule. Yeah, so we also have another system where you can do long horizon planning across contacts. So this is a hopping leg which is mounted on a boomstick, which you can which you can use to study parkour behaviors. So here you see the robot jumping over a single obstacle, and here you have a much wider obstacle, so the robot cannot potentially jump over it. So it uses it as a foothold. And now we define some obstacle course, and we use mixed integer programming to come up with a time optimal plan for where the robot should put its foothold in order to complete this obstacle course. And there are places where the robot can put its feet, and there are places where it cannot. And yeah, it can reason about all that and come up with a policy to achieve this. All right. Yeah, we have been also working on a quadruped on the same lines, so that we can compare such controllers in a fair way also for quadrupedal systems, which is also going to be open source. Okay, now I will talk about the competition. So the task that we proposed in this competition was to swing up and stabilize an underactuated two-link system. So both the Acrobat and the Pendubot variants, and we judged the participants based on the performance as well as robustness of their controllers. And yeah, they were asked to contribute a controller or policy based on any combination of methods from machine learning, reinforcement learning, optimal control, heuristics, and compete on our leaderboards. So the whole competition was divided into 2 steps. We had the simulation stage and the real system stage. So we had about 30 teams that were interested in the simulation stage of the challenge. We selected 4 teams at the end of this stage, and then these were given a chance to participate on the real experiments, real system experiments, and I will talk about their performances in this presentation. So what was provided to them was this software framework where we had like a plant available, an abstract controller class from which they can inherit their controller. We also provided the benchmarking class, modules for system identification, and the connection to the hardware motor control loop. We provided a scoring system for judging the performance of the controller, and these included different criteria like the success of the swing up, because this is already a very challenging problem to bring the double pendulum in the upright unstable posture. Then we had the swing up time, how much energy the controller is consuming to reach there, what's the maximum torque that was used, the integral of the torque, so the time integral during the whole motion, then the cost related to the a quadratic cost on the used torques, how smooth are these torques, because if you jump between the max and min rapidly, then you have a very jerky controller, and also velocity cost. And all these cost terms were combined in order to come up with a final score. Similarly, we defined a robustness score because we believe both performance and robustness are equally important for a policy or a controller. So here we had several components. For example, how robust is the policy to model inaccuracies, then measurement noise, so to the noises in velocity and torque measurements, and also the torque response and time delays. And again, we had a weighted sum of all these costs, which was used to compute the RealAI score. So at the beginning of this competition, we already provided the teams with, I think, 5 different controllers that you can see on this leaderboard. So they were meant to be the baseline or seeds for the teams to implement their own learning-based controllers. And here you can see the performance of these controllers. Some of them, they perform already very good. So I think this ILQR Riccati gains achieves a score of 0.831, and it's a model-based approach. For PenduBot, because it's also in a little bit easier system, you see that it achieves even a higher score. Then we also provided the leaderboards for the robustness scores. Here you see a comparison again, and here we find the TVLQR was the best performing controller with a robustness score of 0.861. For the Acrobat and for the PenduBot, it's 0.950. So at the end of the simulation phase, we had so as a result of the simulation phase, we integrated the contributions into the leaderboard. So here you can see the SAC LQR. This is a contribution from Chi, who is in the audience. Then we have MC Pilko, which is from Nicolo's team. And yeah, this is Acrobat. Yeah. So some teams only submitted controllers for PenduBot. So here you see only 2. And you can see the performance of these new controllers. So we can see that MC Pilko did remarkably well. So it achieved a score of 0.869, which is even better than the model-based controller that we had as a benchmark, which was quite impressive. And then for the PenduBot, we had, in addition to those 2 controllers, we had a controller based on DQN, and which also achieved a good score of 0.815. These are the leaderboards for the robustness score. So here, again, you can see how well these controllers performed in the presence of disturbances. So I think at the end of this simulation phase, TVLQR remained the most robust controls with a score of 0.861, but nevertheless the contributed controllers were also quite good already. So for example, MC Bilko achieved a score of 0.595. And this is the PenduBot simulation robustness leaderboard. And here again we can see that SAC-LQR, for example, achieved quite good robustness score, but again TVLQR remains the best performing controller. Based on the results from the simulation phase, we invited some teams to try this on the real hardware via remote experimentation. So we provided access to the teams via SSH to our real system so that they can test their policies. At this stage, 2 teams decided not to test because they were not confident about the robustness of their policies on the real system, but 2 teams, they proceeded with the experiments. And we have MC Pilko here, which performed almost as good as the model-based control with a real AI score of 0.817 on the Acrobat. So it's clearly the winner of the competition in this Acrobat category. For the PenduBot, we had also the SAC-LQR controller, which worked. So this is the contribution from Chi, but it was not as robust as the MC Pilko. And what we see here is that MC Pilko is even better than our baseline, which is 0.547, which is a TVLQR controller. So again, in this category also, MC Pilko is the best performing controller. So congratulations, Nicolo, for this nice contributions to the competition. Okay, with this, I will conclude my presentation. Just to summarize, like athletic intelligence is still a hard topic, and we are still trying to replicate this on our robots, and try to reach the performance that we find in the nature. And there are a plethora of approaches and opinions in the robotics community, and we believe that one way to find maybe the truth is to test this on real world systems and compare them in a fair and reproducible manner, just like we do science, right, in natural sciences domain. The RealAIGym project provides end-to-end open source systems. They are well documented. They are canonical in nature, so you can often find their equations, their description in textbooks. We already provide, in many cases, state-of-the-art controllers implementation. I mean, whatever is relevant for that particular system. We have a unified benchmarking system for evaluating the athletic performance and robustness. And then we provide online leaderboard with GitHub Actions to check the contributions of the community. And we also soon plan to provide remote access to our hardware so that people around the world can log into the system and use it. And you are most welcome to contribute to the already open source projects, and please spread the word. And with this, I would